So let's see where some of these function families get used. So we're going to work through a few problems together, and then you'll have just a few to do after the video. So the first one is Thrifty started a bank account with $100. Each week, he deposited $20. So I'm going to define the variables, and this is the only one that I expect that you could write the function rule. So B of W will be the balance in dollars, and W is going to be the number of weeks. Can you please stop and write the function rule? Come back when you're ready to check it. All right, so if we start with $100, that's kind of our initial value, and then we're going to add 20 per week. And did you write that the function rule would look something like that? By the way, that's the same thing as if you put B of W equals 20W plus 100 because of the commutative property of addition. Next question, look at your function rule. What type of function is this? So family name over here, absolute value, linear, quadratic, cubic. What kind of function is it? Okay, and did you say that it is your linear? Okay, so before we move to these other questions, we're now going to do the graph. I'm going to get the domain and range, the x-intercept, and the y-intercept off the graph, and then we'll revisit this one at the end. So now, what you need is a piece of graph paper, not coordinate graph paper, because we're only with real-world problems most of the time just using quadrant 1. So you're going to take a piece of graph paper, you're going to draw a y and an x-axis, and make it look like this one. And then you're going to create, some inputs and some outputs, and you're going to graph this situation. So what I would do now is we're going to pause the video while you do that graph, and then we'll come back and see if your graph matches mine. All right, so let's see your graph. Now your inputs might be different. Of course, notice I didn't use the FATE5 because we're not going to talk about -2 weeks or -1 week. So I am going to start with 0. I always like to have that 0 to anchor the graph to the y-axis. And if we put 0 in, of course, that was his initial amount. You might have used 3. You might have used 7. And your values might be different, but your ray should look the same. And what I mean is there should be no arrow down here because you're not going to go into the negative weeks. And then as you plotted your points, they're not going to fall always on the crosshair. So you're doing your best to get them exact. And there should be an arrow out here because this is going to continue potentially to 10 weeks, 11, 12, and so forth. Okay, now that we have the graph, we can go back and answer domain, range, x, y-intercept, those kind of questions. But before we go back to that screen, let's look at the domain, what x's can go in. Notice we're going to start with 0, and then it could go forever. And notice what y's, or in this case, B of w's, can come out. And notice 100 is the bottom of our range. Also, x-intercept, not happening. Y-intercept, 100. All right, let's go back, and if you need to pause and fix, please do that at any time. All righty, so our domain and range, we just kind of mentioned. Our domain is going to start inclusively at 0 and go on forever as far as we know. And the range will start at that initial $100 inclusively and go on forever as well. Remember we said that this ray doesn't hit the x-axis, so there is none. Be careful, don't put 0, like the number 0, because otherwise you're saying it hits at 0. And the y-intercept would be the 100. Okay, so what is the balance after 20 weeks? Well, we cannot use our graph because we didn't have our graph go up to 20 weeks, but we can use our function rule and substitute the 20 in for W, 20 times 20, add the 100, and you should get $500. So there's an example of a linear family real-world application. All right, let's move on to a different family. The population of Whoville was 10 in 2010. Since then, the population has doubled every year. We're going to let P of X be the population, the number of Whovillians, and we're going to let X be the number of years since 2010. It's not the year, it's the years since 2010. We actually could have written this one from our Unit 1, but I am giving it to you. There's our initial amount. You might remember y equals a times b to the x. So our initial population is 10. The doubling would have a growth factor of 2 and raised to the x. And remember, x is going to be the number of years since 2010. All right, what function family does this belong to? And did you say exponential? And remember, domain, range, all of these questions, we're going to take a look and see if our graph will help us. So we're now going to graph this one. Again, as we graph it, we're going to be using regular graph paper. So you're going to make a y-axis and x-axis. Put your title and your years. This should really say years since 2010, now that I think about it. And this would be population. So if you could just fix that for me. Now you're going to put in some, reasonable domain values and do the math. And remember what you think the graph should look like. So pause the video right now and graph this one, and you're ready to come back and check it against mine. Unpause and we'll go. Okay, so let's see the graph here. So I always going to put the 0 in. Anything to the 0 is 1. So, there's that 10, that initial 10. Wow, Mrs. Woodruff, you use some big numbers here. Well, remember, exponential is going to grow pretty rapidly. So after 1 year, doubling would give me 20. After 2 years, it would be 40. And by the way, you can do this in the calculator and you'll see. Now, I did beyond the 4, and you'll see why in a second. But here, I plot the points, and I'm getting that exponential curve. There should be an arrow here. There should not be on this end because we're not going to go back in time. We now can answer domain, and we can answer range. So the domain is going to start inclusively at 0 years, basically at 2010, and then it's going to go potentially forever. There's nothing stopping us right now in that problem. And then our range would start with those 10 whovillions and go up from there. What is our x-intercept? Not happening. And what is our y-intercept? The 10. So let's go back and fill that in. And again, you can be doing this on a notes page. You could be doing it on paper. So we just mentioned the domain and range. I'm just going to show you that. X-intercept wasn't happening. Y-intercept was the initial amount. Okay, so you have a choice here with the population of 2015. That would be 5 years after. So, putting that 5 in, 2 to the 5th times 10. And you'll notice that I had actually done that on my table because I saw that question coming. When you double the 160, it will be 320 when you put in the 5, or when you kind of look at your graph. Harder to pull off the graph. Always easier to use the rule. Are we okay with our exponential example? So exponential growth of population is a real-world example of an exponential graph. Let's go beyond. All right, here's our next family. A rock falls from a 1,000-foot cliff. H of t is going to be the height of the rock in feet, by the way, because you can see that up here. And the time will be in seconds, and t will be our input variable. We cannot write this one at this point, but I promise after Unit 8, at the very end of the year, you will do this on your own, but I'm going to give it to you for right now. All right, what type of function is this? Name the family, look at the rule. And did you say that it is a quadratic? You should already have an idea of what the graph is going to look like. Think about what that negative is going to do. What's the shape of the graph going to be? What's the 1,000 do? Remember, we kind of talked about that a couple of videos before this one. Again, for domain and range, I'm going to wait until I have the graph. So I'm now going to make a table and graph this one. Okay, we're going to head over to our graph paper again. We're going to put a y and an x-axis. We're going to create this picture. We're going to call it the falling rock. Our input is time in seconds, and our height is going to be height in feet. And you can use my range of numbers here. I've got the x going by ones, and I've got the y's going by 100 for each block. Once you've done that, we're going to create a table. Fave 5 are going to fail us here because we're not going to use the negative inputs. And by the way, that's the good thing about our applications. We often get away from those negatives. So I'm going to start with a 0, and we're going to put in some values, make a table, give it a graph here, and let's see how you do. Pause it, come back when you've got your graph, please. Okay, let's see how you did. So 0, 1,000, 1, 984, 2 is 936. So again, I'm coming up here, for instance, with 2, and I'm squaring the 2, which would be 4. I'm multiplying by -16 and adding to 1,000, and you're going to know it's going down, which is what we expect due to gravity. Now, I kept going here because I wanted to see when it was going to hit, and you'll notice that at 8 seconds, it would be underground, basically. So it's hitting just to the left of 8 seconds, maybe 7.9-ish. Again, we will be able to do that kind of math in Unit 8, but right now we know it's just shy of the 8 seconds. All right, so there is our graph. It is half of a parabola. The other part of the U is hanging out in negative land, which in this case doesn't make sense. Our domain for this problem is we are going to start at 0 time, and we're going to end just before that 8 seconds, right? And our range would be basically, from 0 feet to the 1,000 feet that it started. X-intercept, just shy of 8 seconds, and our y-intercept is 1,000 feet. Again, pause at any time you need to, but I'm going to go back to fill in those questions that we saw on the first slide. So our domain and range we just mentioned. I'm calling it 7.9 seconds. So from 0 to 7.9 seconds inclusively, you could really put an 8 here with a parenthesis, and I would accept that as well. The range definitely has to agree with mine. And don't put the 1,000 on the left, even though it started there. Your range should go in order of the number line. So inclusively 0 to 1,000 feet. The x-intercept, is about that 7.9, and the y-intercept is a definite 1,000 feet. What is h of 2? What does that mean? So in our function notation, what does that mean? Well, what it does mean is that we're going to have 2 seconds. What was the height at 2 seconds? And you're going to put that 2 in, square it, multiplied by -16 times 1,000. I think I used that on my table. But the rock after 2 seconds would be 936 feet off the ground. So this is an example of a quadratic family. Going to move on to our 4th example here. Again, an application. In this case, you're climbing up a 500-foot observation tower. If any of you have ever been to Groton, to Fort Griswold, you could think of the monument there. But anyway, you're going to be climbing an observation tower. The tower is 500 feet. And the question is, how far can you see to the horizon, on a clear day? So D of H is going to be the distance to the horizon in miles. That's how far you can see in miles to the horizon. And H is going to be your height off the ground in feet. So the higher you go up, the farther you can see. And I'm going to, again, give you this function rule. We will not write this one this year, but your distance that you can see to the horizon will equal 1.22 times the square root of the height that you are off the ground. And this is true. So what type of function, what function family would this be? And did you say square root? What are the domain and range? Got to do the graph, right? So again, we're going to take a piece of regular graph paper, and we'll come back in a second to answer these questions. So how far can you see? The height off the ground in feet is going to be our x, and the distance that we can see to the horizon in miles will be our y. And if you, again, just make a quick y and x and just do this graph, then put in some values and see what you get here. And once you've got that graph, come back. Let's see how you did. So here's the graph. You're going to see I've put, some perfect squares in there. The reason I'm not seeing, the integers or whole numbers over here, I should say, is because I'm multiplying by 1.22. But you would take the square root of 25, which is 5, multiply it by 1.22, and you'd see 6.1. So if you're 25 feet off the ground, you can see about 6.1 miles to the horizon. So basically, I went up and included the 500 because you're going to remember the tower is 500 feet tall, so you can't go beyond that. And so this would be the maximum input, and this would be the maximum output for this example. Now, Mrs. Woodruff, why did you put an arrow there? Because I can't, on my graph, the way I put the intervals, I can't reach the 27.3, so I still have a ways to go. So yes, it is half a parabola, which we expected for our square root graph. And let's look at our domain and range. So the domain is going to go from 0 being on the ground, and it would stop at 500 in this example. And our range would go from 0 that you can't see to the horizon, which, you know, we can see a little bit. But anyway, you wouldn't be able to see a full mile. And then our maximum range would be the 27.3. So let's go back, and again, pause anytime if you need to, but let's go back and just fill in those questions. So, you know, there's the domain and range we talked about, and it would be inclusive on both ends with the brackets. X-intercept 0, and the y-intercept would be 0 mile. You'd actually see less than that, but from a mathematical standpoint, there it is. So last question here, what is d of 225 minus d of 100? So the first thing you're going to do is you're going to put 225 in and get a value and set it aside. You're going to put the 100 in and get a value and subtract them. And then I want you to think about what that number means. So first of all, numerically, did you get 18.3 minus the 12.2, which would be 6.1 miles? What does that mean in terms of the tower? Basically, if you are at 100 and you go up to 225, you will have an increase of 6.1 miles more visibility. So when you go up that 125 feet, you can see 6.1 further miles. All right, that was the square root. So now what I'm going to do is give you another example of basically a step function up here. I kind of gave away the answer. But when you go into the post office, for the first 3 ounces, greater than 0, obviously, otherwise you don't have a package, and up to 3 inclusively ounces, you would pay like $1.95. And then anything above the 3 and inclusively 4 jumps to $2.12 and so forth according to this table. So my first question would have been, you know, what function is this? And it is a stem function, which does get connected to the greatest integer function, although this time they're not integers. You know, the numbers are integers. It's still that same idea. So what I'm going to ask you to do is to see if you can graph this one yourself. And again, it would be on regular graph paper with an X and a Y. You're going to make steps and see, you know, one of the steps here, I'm going to warn you, one of the steps is longer, and this is real data. So up to 3 ounces, you're going to pay the $1.95, and then it will jump to the $2.12. So go ahead and see what you can do with this graph, and then we'll come back and we'll check it. And this one was a big concern in class, so you know, take it seriously and give it a try here. Okay, so let's move forward. So basically, you know, U.S. postal rates, and I'm, you know, going up by, I start kind of at $1.50 and then $1.75. So I kind of have a break in the graph. And then I'm going up, 2 blocks is 50 cents. So each block is 25. And then I've got the ounces going this way. And there is a break in the graph here. Cost in dollars is going to be your Y label. The number of ounces is your X, and I'm calling it U.S. parcel postal rates. So you should have gotten steps. So that first step was at the $1.95-ish, right? That's where I'm putting it. You don't have a cost for 0. And then it will go up, and including 3 ounces, you would pay the $1.95. Now, the minute up here, anything above, so I'm going to put the open circle. This would be the $2.12. And then it's going to go up inclusively to 4. So actually, this is kind of an example. People asked me in class about a step function and would it kind of go the other way. Here's a real world example where the fill-in is on the opposite end of the step. It's not really a greatest integer function, but it mimics that kind of idea. And then the steps from that point on will look the same at the respective cost, basically. So that is a step function. I'm going to call it a greatest integer function in quotes, but the output is not integer. So there's an example of a real world step graph. One last one, guys, is going to be our piecewise, but I just want you to look at this step function, and it's also going to pertain as we go forward to our piecewise. But if you have an unbroken function, if you can trace the function without picking up your pencil, that is called a continuous function, and we've seen that word before. Now, when the function breaks and you have to pick up your pencil to draw pieces of it, it actually has another name in calculus called a discontinuous function. So continuous versus discontinuous. And I thought I'd just throw that word out there. So step function is a discontinuous function. Speaking of discontinuous functions, piecewise can be discontinuous or continuous if they are, broken or not. So we've just been having trouble with a little bit with the step and the piecewise. I don't really have a real world example behind this one, but I thought we would do one more. So we're going to go back to our coordinate graphs and do a piecewise just to give it one more practice time. So I'm going to ask you to, the video is going to stop, and I want you to graph this one, and we will come back again. This is our piecewise. We're expecting 3 pieces. Now, will they connect or will it be discontinuous? We will see. But I can already see what this piece should look like. This one is just, that's interesting. And one there, see what you can do with this one. Come back and check it. All right, so to finish with our piecewise today, let's see how you did. So for all values less than 2, which would be all of these, we would be on this parabola right here, right? And if we were to put 2 in here, it would be 2, 4. So 2, 4 has an open because we're not allowed to, by our domain, put the 2 in, but it kind of gives you an idea of where it ends. The next one is just a point. When 2 goes in, 6 comes out. There's the point. And then the final piece is going to be a line for all numbers bigger than 2, right? So 3 would be 7, 4 would be 6. But where does the line start? So I'm going to illegally put 2 in. 10 minus 2 would give me 8. So 2, 8 is where it would start. So that's why there's an open circle, and there comes my line with the points that I put here. Now, is this continuous or discontinuous? Pretty easy to look at it and see that you have to pick up your pencil to draw it. It's a discontinuous function. So today we saw kind of examples of where some of these function families are represented in the real world. And I also just gave you another review of a piecewise since that was a bothersome one. Guys, next thing up is just to do a couple of these yourself, 4 examples yourself, and then we're on to the study guide, heading for the Unit 3 test on functions. I hope you guys have a great day. See you soon.